It is my honor to give a presentation today. I am Ken Sugimori, and our topic is avatar tracking control. In our research, like this video shows, we use avatars manipulated by motion capture. Recently, the avatar application become more and more popular. For example, social VRs, multiplayer online VR games, virtual YouTubers. With avatars, we can chat, do sports, play game. In these avatar applications, there are problems. Avatars are not affected by contact. In conventional method, when an object collides with an avatar, like this, the avatar does not move. And when avatars comes into contact with each other, like this, it is hugging, they penetrate. Currently, avatar applications are challenging to these problems. For example, we can grab hair, but if the motion captured bones, such as hand or head, collide with each other, the behavior will be unnatural. The goal of our research is write videos. When an object collides with an avatar, like this, the avatar moves by collide. When avatar comes into contact with each other, avatars do not penetrate, like this. The reason of these problems is only object movements are physically simulated, while avatars' movements are not. To solve this, some studies switch to physics simulation during contact. However, this method cannot be used in our case because we are assuming constant contact, such as hugging. So we will make the physically simulated avatars track the performance movements. In basic avatar tracking control, PD control is used. PD control is a control like spring damper. Here we represent PD control with a spring damper. We attach a spring damper to each joint, and it will pull the joint to target angle. For soft reaction, weak spring damper are used. But weak spring damper cause large tracking delay and overshoot. Like this video. Left is input and right is output. You can see the delay and overshoot. Next is purpose. We assist. The purpose is to assist users in performing natural avatars movement for contact by physics simulation. In particular, we aim to achieve quick tracking and soft reactions. In field of robotics, there are ways to solve tracking delay and overshoot. The procedure is first to set up a robot's equation of motion. Tau is torque, and Q is joint rotation. Then, by inputting the target movement for q dot dot, we can calculate tracking torque. Calculating the tracking torque is called inverse dynamics. This figure is the flow. Inverse dynamics calculate the tracking torque tau f, and the system adds tau f to a robot whose joints are weak PD controlled. But this inverse dynamics is troublesome because the equation of motion are created manually. In our case, when the structure of the character changes, the equation of motion changes. So we did a previous research. This is our previous method. We used strong PD control for inverse dynamics. This method does not need to set up the equation of motion manually. Another difference is the target of control. In robotics, the target is robot in actual world. In our case, the target is avatar in simulation. However, our previous method have a problem. Our previous method causes tracking delay due to iterative solver calculation error for PD control, like this video. Red is input and blue is output. It is delayed and shaked, like this. To solve this, I propose this system. For inverse dynamics, we used the Newton-Euler Formulation, which is formulated to deal with changes in the structure of characters. By Newton-Euler Formulation, the input and output overlap like this. The avatar is tracking accurately. Next, I'll explain how to calculate Newton-Euler formulation. The procedure is first calculate the acceleration ACC of the rigid body and convert it to the target tracking force F using Newton-Euler equation of motion. The acceleration formula looks like this. The key point is this formula is also used in simulation, and accurate tracking can be achieved by using the same formula. Next is right parts. By weak PD control and physics simulation, like this video, a soft reaction can be achieved. Next, I will explain the method used for physics simulation. For simulation, we use a physics engine that automates the equation of motion. There are two common methods for setting up equation of motion. Maximal coordinate method and reduced coordinate method. I will explain this method first. Maximal coordinate method. Left figure. This method set up a motion for the 6 degree of freedom, position and rotation of a rigid body. And like right figure, the joints are realized by calculating constraint force. Second method is a reduced coordinate method. This method sets up equation of motion for degree of freedom Q of the joint, like this. This method don't calculate constraint force. We used reduced coordinate method. There are 3 pros in this method. The first is correct velocity. In maximal coordinate method, the rigid body velocity is linear. For example, if we fix a left rigid body and apply force, upward force to right rigid body, reduced coordinate method will calculate the correct velocity, such as circular motion around the joint. However, with maximal coordinate method, the velocity will be upward. This is wrong velocity. This happens because Jacobian that converts joint velocity to rigid body velocity is not updated during one step to solve processing time. Second pro is no constraint force error. In maximal coordinate method, there is an iterative calculation error in the constraint force of the joints. In reduced coordinate method, the constraint force is not calculated, so there is no error. This figure is about maximal coordinate method. The red is target pose, and when we apply the tracking force and torque with the proposed method, if there are no joint, the posture will be shifted like this. However, if we make the joint with joints, the constraint force will be calculated and the posture will be corrected. However, because there is an error in the constraint force, the target posture will not be achieved accurately. In maximal coordinate method, it is difficult to achieve accurate tracking. Third pro is same formula into inverse dynamics. The acceleration formula used in reduced coordinate method and the Newton-Euler formulation are the same, like this. Using the same formula, high tracking performance can be achieved. Next is evaluation. We made 2 evaluations. The first evaluation is trackability evaluation. We will compare the trackability with 3 methods using same input motion. The input motion as is right below. Turnaround movement. In turnaround, there is a tendency for tracking delay because the whole body moves a lot. And turnaround is common movement in current avatar application. This is the result. The time for one step is 2 milliseconds, and the step execution cycle is once every 20 milliseconds. Works in real time. Maximal and reduced are previous method. like this. We can see the maximal and reduced have tracking delay. In proposed, input and output are overlapped because they are tracking accurately. Moreover, to clarify the delay, I measured the angle. This is an angle graph of difference between the joint rotation of input and output of a rigid right hip joint. Green is proposed method, and blue and orange is previous method. Previous method have difference between input and output, while proposed is almost zero, like this. A proposed tracks accurately. A second evaluation is fixation of both feet. Previous method fixes the waist to reduce the joint tracking torque, which speed up the convergence of the iterative calculation, while the proposed method fixes both feet. In order to evaluate the difference in motion, we performed the same motion. The motion is crossing shoulder and swaying. This. In the previous method, the feet are not fixed, and so the feet slips. In the proposed method, the feet are fixed and the feet do not slip. Fixation of both feet makes more natural movement. In summary, the proposed method can assist users in performing natural avatars movement for contact by physics simulation. In particular, accurate tracking was achieved in a small amount of computation time that can operate in real time. Furthermore, fixing the feet prevents the feet from slipping, and the motion becomes more natural. That's all. Thank you.